This is the beginning of many reactions that we're going to see in this chapter of alkenes reacting with various things. What we're going to cover in this short lecture is halogenation and hydrohalogenation. In halogenation, we add halogens across a double bond, and in hydrohalogenation, you see the hydro, we're actually going to add the halogen and then add water to it. If you have the halogen by yourself, then you just have halogenation, and water doesn't get involved. But if you add water to the reaction mixture, you do not get halogenation. What you do is you get hydrohalogenation instead. So let's go ahead and look at this reaction and look at what we're talking about exactly. Halogenation, what we're going to do is look at chlorine or bromine adding across the double bond. Fluorine we don't do. It's a highly exothermic and kind of uncontrollable. And iodine we don't do because it's so reversible that it adds and then it unadds very quickly. This is an oxidation step because what happens is the carbon goes to being bound to itself in the double bond to being bound to an atom with greater electronegativity, so it basically is taking electrons away from the carbon, so the carbon's losing electrons. We actually look at oxidation and reduction differently in organic chemistry, which we'll look at later on. But for now, just trust me that this is oxidation. And you can actually draw the halogen. No, this would either be chlorine or bromine in these spots. And you can draw them across from the double bond like this. This bond's going to break, and one of these double bonds is going to break, and then the halogen becomes, each of the halogens then become attached to carbons that used to be in the double bond. Now, this is not the mechanism that I've just shown you here. Keep that in mind. I'm just showing you a simple way of figuring out how do you get the product of this reaction. A dihalide, meaning two halogens are attached to adjacent atoms. A dihalide is the product. We call them vicinal dihalides. Vicinal means on adjacent carbons. So we have a dihalide is the product. And what we're going to find is that hydrogens add anti to each other. Now, you don't know what that means, but in a little bit you will. Okay. Halogenation occurs in this way. Here is a bromine. The same thing would happen with chlorine, looking almost identical, except you would have chlorines here. But the bromine comes and is attracted to the electrons in the pi bond here. The pi bond electrons of this carbon-carbon double bond reach out to right here and form a single bond between this carbon and this bromine. And then the bromine non-bonding pairs actually reach down and form a bond right here. As that happens, the electrons here jump onto the bromine to make bromide over here. Notice this makes a positive ion on the bromine, and it is in this what looks like a cyclopropene ring, except it's got a bromine at one corner of it, and this is called a bromonium ion. It is a relatively stable intermediate. We can detect it, but it is an intermediate. It doesn't stay for long. What happens is the bromide comes in from underneath and forms a bond with one of the carbons, and then the electrons that are in the bond to the bromonium ion right here, they break and jump onto the bromine positive ion to become neutral. And so what you see is one bromine adds on one side of the double bond, and the other bromine adds on the other side of the double bond. Just to start, what you need to be able to do is take an alkene and just place those bromines in the proper place. Notice, here is the double bond. One of the bromines ends up on one side, the other bromine ends up on the other side, and you have the loss of the double bond. There's just a single bond now here between these two carbons. And so this is the first step for you to understand that that double bond is broken. One bromine goes on one side and one bromine goes on the other side. Right here, we're not worrying about anti-addition because you can't even see it with this symmetrical molecule. But I want you to understand this first step right here. Now, if we want to see how anti-addition occurs, we can take a molecule in which one side of the double bond is different. Do you see how it's different on this side? It's got this on one side, this part of a one-membered bridge on one side, and on the other side of the double bond, you got a two-membered bridge. So if I have something coming underneath, it would be different from something coming on top. Okay, so what happens is when chlorine adds to one side to form a chloronium ion, just like the bromonium ion, then the chloride is going to come, if the chlorine is adding from this side, then a chloride will come from underneath. Or if the chloride adds from underneath, a chlorine will come from on top. What happens is one chlorine then ends up going to one carbon and the other chlorine goes to the other carbon, but you notice how they're on opposite sides of that double bond now? That's what's called anti-addition. Let's look at it with this molecule here, cyclopentene, and we're going to draw it so that it looks like it's planar. Think of this part of the ring going back behind the page and the hydrogen's coming out at you kind of like flat as you look across it. So now, this is how you visualize this happening. This bromine can either come in from this side with one bromine down and one bromine up, or the bromine can come in from this side, one bromine going up and one bromine down. It adds and makes a bromonium ion. This three-membered ring would either be down with a bromine here, or it could be up with a bromine up here. Regardless, you're going to get the same product, because bromide, if the bromine's up here, the bromide's going to come from underneath and flip that ring open to put the bromine on the other carbon atom. So one bromine here, one bromine here. Or if the bromonium ion is down where the bromine is down here, then you're going to have a bromide come in from the other side, and what will happen is that'll snap that three-membered ring open and put the bromine on one carbon, and then the bromide that's coming in is going to attach to the other carbon. Regardless of how you try to look at this reaction happening, what you're going to get is the trans addition. This is an anti-arrangement of the bromonium ion on one side and the bromide coming in. Gives trans all the time. It's the anti-addition causes the trans product to be formed. You never form the cis because that would require syn addition, them two coming in on the same side. And anti is the only way that this reaction occurs. So here is a picture of what I just described to you. The bromine coming in from one side. Okay, that forms a bromide, and then it comes in from the other side. And if it comes in on this side, that snaps open this way. Or if the bromine were to come in over here, it would snap open that way. Now, you can actually see there would be two different products formed. They would be enantiomers. One would be with bromine down on this side and bromine up on this side, or the enantiomer would be with bromine down here and a bromine up there. They would be mirror images, and this is what we see with a chiral product reacting with a chiral product. A lot of times they make enantiomers in a 50-50 racemic mixture. And usually we'll just draw one unless the question says draw, both stereoisomers or all the stereoisomers or whatever, or how many products are formed. Each question you have to look and see what is it asking for. But realize you have what? Anti-addition, and on this ring compound, it gives a trans compound. So go ahead and draw the product of each of these two reactions, and then restart the lecture after you have figured this out. Okay, the product of this, you see you have the two methyls here. So one bromine will be down and the other one up, or if you had this bromine up and that one down, that's great too. The key thing is they have to be trans, the bromines have to be trans to each other. What about this compound? In this compound, because two groups are the same here, you're not going to be able to see a difference. This carbon here is going to be achiral. Right here is achiral. Now this is a chiral compound. You can detect a difference here, but what would you see? Enantiomers would form. But what is a key thing for you to be able to do at this point in time? With time, you're going to be able to figure out the enantiomers and things. That's kind of challenging for you right now. The key thing for you to get is if there's a ring or the double bond is somehow where you would see a difference, make sure that you put your bromines or chlorines in an anti-position. Here, you don't have to worry because there's no anti-position cannot be seen. So what do you have to make sure of? That you identify the double bond, you reduce it to a single bond and add chlorine to one carbon and a chlorine to the other carbon, which is what the product is here. Okay, now, halohydrin formation. If, when you have your chlorine or bromine in the reaction and water is present in that reaction, what happens instead of a bromide or a chloride opening the bromonium or chloronium ring, water acts as the nucleophile there. If I look at this, I would have the halogen would form, you would form, let's say, a bromonium ion here, then water would come in from underneath to open the bromonium ion. And so what you get as a product of that reaction is a halogen on one carbon, and you get an alcohol group on the other. And there's also some hydrohalic acid that's formed as a side product. Let's look at this a little bit more in depth. Here's the mechanism. Okay, so here is a double bond. You notice the methyls are trans to each other. What's the first thing that happened? That bromine dives in and forms a bromonium ion. Notice here it is. And there's a bromide that comes off when it forms. Notice this is trans. So once it adds a bromonium ion, notice how the methyl group is on the opposite side of that methyl group. Do you see how it's retaining this trans configuration in the formation of this bromonium ion? Now what happens is water is going to come in from the other side and open this bromonium ion. So here it comes in from underneath, and then this pops open, and you get the bromine over to one side. And now you have water attached to the carbon that used to be on the other side of the bromonium ion. This water, notice that when you have electrons leave to form this bond, that oxygen now is going to have 1, 2 hydrogens on it. Notice it has 3 bonds, so now it has a positive charge. Notice from here to here, we have charge conservation. Neutral, the two of these things together are neutral. Now, if I look at the water and this, and I add up all the charges, you'll find it's neutral. Now I go down here, and you can see here is the bromide is not written, but it's still there, so it's over here. But if I just look at this part being reproduced down here from the ring opening, you can see this part is positive. So this is positive. Where is that positive charge? On the oxygen, because it has 3 bonds. And an oxygen with 3 bonds must have a positive charge. Now, there's lots of water floating around, and what does it do? It grabs that proton to make a hydronium ion, and those electrons jump onto the oxygen to make it neutral. And see, here it's neutral, and there is the production of the hydronium ion that we're getting from this. Okay, so let's look at this with what happens with these two compounds. We've seen that we have with halogenation, we see that the bromonium causes anti-addition. So one bromine will be up and the other down, and you get anti-addition. And you're basically seeing the same thing here because the water's attacking from underneath. So what are we getting? We're getting anti-addition again. See that anti-addition right here? Okay. And so then what happens is we get a chiral carbon here and a chiral carbon there. And these two are always going to be this, the stereochemist that we see here will be this or the mirror image. So when we look at the outcome of this reaction, we never find a diastereomers of this. Why? Because it's always going to be this or the mirror image due to anti-addition. Notice, because the bromine opens up slightly to put a positive charge on a carbon, what we're going to actually get is that positive charge will reside on the more substituted atom, so you get the oxygen attacking there. You can't see it with this compound because this is a symmetrical compound, but we will in the future, and I'll show it to you. Don't worry. And so this is a part of the mechanism that you're going to need to know, but we're going to see evidence of it in future reactions. Okay, so here's an example. Notice this carbon is different from this carbon. This carbon has 2 methyls on it. This only has 1. So when the bromine adds to this, it's going to make a bromonium ion, and that bromonium ion opens up slightly to put a positive charge on one of these carbons. Because this one is tertiary and this one is secondary once you have, for ring opening purposes, the positive charge will end up here and then water will attack there. So what do you need to know from this? The key point you get from this is that when you have hydrohalogenation, the bromine ends up on the less substituted carbon and the hydroxyl group ends up on the more substituted carbon. And we say it is Markovnikov addition for the hydroxyl group. Key point here. You cannot see the anti-addition is still happening. The point of this reaction is to demonstrate the Markovnikov addition for the hydroxyl group. So you see bromine on the less substituted atom and the alcohol group on the more substituted atom. Here's another example. Here what I'm going to show you is how anti-addition occurs. Notice the substitution is the same, so these two carbons are equivalent with regards to ring opening and where the hydroxyl group goes. It doesn't matter which one you put it on. But notice this reaction is demonstrating how you have anti-addition, chlorine on one side and hydroxyl on the other. That's the anti-addition that you always see with hydrohalogenation. So you've seen two things with hydrohalogenation that you need to remember. One is that the hydroxyl group ends up on the more substituted carbon. Second thing, you have to have an anti-addition. So what have you learned in this online lecture? Two things. You've learned about halogenation and hydrohalogenation. The conditions for halogenation are either bromine or chlorine with an alkene, and typically the solvent that we use for this is carbon tetrachloride. When we do this, it adds 2 chlorines or 2 bromines across that double bond. One adds to one carbon and the other to the other carbon. The double bond is lost and you have anti-addition occur. With hydrohalogenation, what are your conditions? It's bromine with water as a solvent or chlorine with water as a solvent. And of course you have to have an alkene. To the double bond, you add a chlorine or a bromine to one carbon and the hydroxyl to the other. The chlorine adds to the less substituted carbon and the hydroxyl adds to the more substituted carbon. So we say it's Markovnikov for the hydroxyl group. The double bond is lost and you get anti-addition. So now you go ahead and try to apply these principles to the following problems. What is the outcome of this reaction? Okay, the outcome of this reaction is this dihalide. You have chlorine is added to each of the carbons in the double bond. The double bond is lost. One chlorine on one carbon, one chlorine on the other. And notice it is anti-addition. The carbon tetrachloride here is just a solvent. It does not participate in the reaction. What is the outcome of this reaction? Well, if I look at this, here is my double bond. These double bonds are not truly double bonds. We're going to see later on that these are called aromatic. They do not react. The only double bond that's going to react is this one. So what happens? Well, we're going to have chlorine add, the conditions are for hydrohalogenation, so we get a chlorine adding to one carbon and a hydroxyl group adding to the other. Which one does the chlorine go to? It goes to the less substituted carbon, and the hydroxyl group goes to the more substituted carbon. So we end up having this compound, this arrangement. Anti-addition occurred, but you just can't see it with this compound, so we don't bother indicating it in any way. So what is the outcome of this reaction? Here we're going to have halogenation of the double bond. Chlorine's going to add to one and another chlorine to the other carbon in the double bond, and we lose the double bond. Notice this anti-addition, so we get chlorine on one side and the chlorine on the other side is anti-addition. What conditions do you need for this reaction? Well, if you look at this reaction, you can see that the double bond is gone and a bromine came in here and a bromine came in here. So what do we need? We need to have bromine as a reagent and not water, but carbon tetrachloride as a solvent. What alkene and what reagents would you need to produce this compound? Well, to do this, you would look and see the hydroxyl group is on this carbon and on that bromine. That means I would have to have had my double bond here. The reagents that I would need would be bromine and water. Notice the bromine went to the less substituted carbon and the hydroxyl on the more substituted carbon.